Imagine a billionaire venture capitalist walking onto a massive stage, right?
Oh, yeah, we've all seen those presentations. The black turtleneck, the dramatic lighting.
Exactly, yeah. The crowd goes dead silent. And he smiles, looks out at the audience, and holds up the small, crystal clear vial of water.
Just water.
Just tap water. And he says, with our new proprietary engine, you can pour this vial into your car and drive from New York to Los Angeles.
Which is such an alluring pitch.
It really is. I mean, he's saying no oil wells, no lithium mines, just, grab a garden hose and you're good to go.
It is, without a doubt, the most seductive energy myth of the 21st century.
The water-powered engine, it just refuses to die.
It really does. And I think, it taps into this deeply ingrained human expectation of the windfall.
The windfall? What do you mean by that?
Well, we are so used to the extraction economy.
Yeah.
Historically, you dig a hole, you strike oil, the pressure builds, and the earth just hands you this geyser of compressed power.
Right, it's just sitting there waiting for us.
Exactly. We're completely conditioned to look for the next magical well.
And because water is everywhere, I mean, oceans, rivers, rain, we look at it and our extraction-wired brains just automatically see a geyser.
We see limitless potential. But today, we're going to completely tear apart that water is fuel illusion.
Yes, we are. We are taking a deep dive into the brutal, beautiful physics of what hydrogen actually is.
Because mathematically, scientifically, when you look at that vial of water, you are not looking at a geyser.
No, you are absolutely not. You are looking at the absolute bottom of an energetic well.
It requires a total rewiring of how you perceive chemistry.
And just to be clear up front, the reality of what it takes to actually extract energy from that system is, frankly, infinitely more fascinating than the urban legend.
Oh, absolutely. It's much more demanding, but the engineering is just incredible.
So, to guide us through this reality check today, we are digging into a truly groundbreaking stack of materials.
Yeah. The core of this deep dive is this comprehensive 2026 manifesto by Philip Lillian.
Published by the UCTE Foundation. It's titled, Water is Not Fuel, a closure-theoretic map of hydrogen energy logistics.
It's a mouthful, but it is brilliant.
And alongside that main text, we're looking at this highly complex series of diagnostic diagrams, schematics, and performance metrics charts.
Right, all mapping out the bleeding-edge realities of the global hydrogen economy.
What makes this specific stack of sources so vital, I think, is that it completely refuses to compromise on the physics.
It really strips away all the startup press releases. It ignores the venture capital hype entirely.
Yeah, it forces us to look at the raw thermodynamics of the water molecule. It's basically an instruction manual for reality.
That's a great way to put it.
And that is our mission for you, the listener, today. If you follow the energy sector, you know there is just so much noise out there.
So much noise.
We want to comprehensively rewire how you think about water, energy, and the true economic role of hydrogen.
We're going to get into the microscopic mechanics, the engineering hurdles, the thermodynamics, all of it.
By the time we finish this deep dive, you are going to have a foolproof mental framework.
Right. You'll be able to instantly spot the difference between a genuine energy breakthrough and scientifically impossible hype.
Which means, I guess we have to start at the very foundation.
Yeah, before we can even discuss building a hydrogen economy, we have to clear the psychological hurdle. We have to unlearn water.
Unlearn water. The sources tackle this right on page 1. They call it myth 1, this idea that water is a primary fuel source.
And, it's easy to see why people fall for it.
Sure. I mean, water forms crashing waves. It cuts through the Grand Canyon. It spins massive hydroelectric dams.
Right. We constantly associate it with life and kinetic power. So why wouldn't it be our ultimate chemical fuel?
Because kinetic power like water falling due to gravity is completely different from chemical potential.
Completely different. The text corrects this myth with a very blunt reality check.
Yeah, it says water is the exhausted product of hydrogen oxidation.
It is spent fuel.
I want to make sure we really nail this concept for the listener. Treating water as fuel is literally like staring at the gray ashes left over from a campfire.
Oh, that's the perfect analogy.
And you're sitting there trying to set those ashes on fire again. You can't extract heat from ash. The heat is already gone.
To get the log back, you would have to pour massive, mathematically impossible amounts of energy into that ash to reconstruct the wood.
Right, and that is exactly what is happening chemically here.
When you take raw hydrogen gas and raw oxygen gas and combine them, when they burn or react in a fuel cell,
they release a tremendous amount of useful energy. They power a rocket or they power a car.
And what is left over from that violent high-energy reaction?
H2O.
Water. Exactly. The energy has already left the building.
The manifesto introduces this highly structured vocabulary to explain this, which they call closure theory.
Yeah, closure theory. It completely changes how you visualize the molecule.
In this theory, water is described as existing in a, quote, deep, stable closure. Can we unpack the mechanics of that? Why is it so stable?
It all comes down to the relationship between the atoms. You have one oxygen atom and two hydrogen atoms.
Right. The classic Mickey Mouse shape.
Exactly. Now, oxygen is highly electronegative. It absolutely loves electrons.
It's an electron hog.
Very much so.
Oh.
And hydrogen is perfectly willing to share. So when they bond, they lock together in this geometric arrangement that is incredibly comfortable for both of them.
So they form this highly stable, tightly bound network.
Right. And because those atoms are so perfectly satisfied in that configuration, the molecule just drops to the bottom of the energetic valley.
It's deeply exhausted. It has no desire to react, no desire to give up energy.
It is in a state of deep closure.
Okay, so if water is the ash at the bottom of the valley in this framework, what actually is hydrogen gas?
Right, because we always talk about it as a fuel.
Yeah, people call it the fuel of the future.
And that's the linguistic trap. Hydrogen isn't a primary energy source that you just go out and harvest, like coal or sunlight.
So what is it?
Hydrogen, in this framework, is defined as separated closure potential.
Separated closure potential. So it's basically a chemical battery.
Exactly. It is a carrier of invested energy, not the origin of it.
Okay, let me make sure I have this. To get hydrogen gas, you have to find that perfectly stable water molecule.
The one that's super happy at the bottom of the valley.
Right, and you have to violently rip it apart. You have to break that deep, stable closure.
And because the atoms really want to stay together, tearing them apart, which we call electrolysis or water splitting, is not an energy extraction process.
But you aren't getting anything out of it.
Not at all. The text actually redefines water splitting as externally powered closure charging.
Externally powered closure charging. So you are physically dragging the system out of its deep resting state.
Pushing it up a massive energetic hill.
And you have to use outside energy to do it.
You are lifting the chemical system against its will. And this right here, this completely destroys the myth of the self-powered water engine.
Oh, because if you have a car that runs on hydrogen, and it makes that hydrogen by splitting water on board the car,
it will always, inevitably, require more electrical energy to split the water than it gets back from burning the hydrogen.
because the universe charges attack.
Exactly. There is no surplus. You are trying to pull yourself up by your own shoelaces.
The system has already descended into its most stable state.
Yeah. To get the hydrogen, you must have a massive external energy source. A dedicated solar farm, a nuclear reactor, a massive wind turbine.
You need that outside power to perform that closure charging.
Right.
Okay, so we've established the unyielding reality. We must input external energy to charge water into hydrogen. We are pushing the boulder up the hill.
There's no getting around it.
But that instantly raises the next crucial question. Exactly how much energy are we talking about?
Which is the million-dollar question.
And is there some clever physics trick that lets us lower that cost? This brings us to the second major concept in the sources, the immutable physics and what they call the thermodynamic floor.
The manifesto provides this stunning, highly detailed visual for this, called the thermodynamic floor diagram.
It's honestly the most sobering chart in the entire stack. It maps out exactly where the electrical energy goes when you force a water molecule to split.
Let's trace this diagram for the listener.
Yeah.
Because it's really striking.
At the very bottom of the chart, there is this stark blue zone. And capping that blue zone is a hard, flat line drawn at exactly 1.23 volts. What is that line?
That 1.23 volts is identified as the reversible free energy floor.
The reversible free energy floor.
Okay, in thermodynamics, this is known as the Gibbs free energy requirement. It represents the absolute mathematical minimum amount of electrical work required to sever the oxygen-hydrogen bonds.
Under standard temperature and pressure, right?
Right.
So just to be absolutely clear on the mechanics here, why is it 1.23 volts? Why not 0 or like 0.5?
Well, because breaking a chemical bond requires you to overcome the electromagnetic forces holding the electrons and protons together.
It's a literal physical force you have to fight.
Yes, that 1.23 volts is the raw thermodynamic toll you have to pay the universe to break the water molecule apart.
To create that separated closure potential we talked about.
Exactly. And the author, Philip Lillian, is absolutely militant on this point. No catalyst, no matter how exotic, can erase this cost.
You just have to pay the toll. But looking at the diagram, right above that 1.23-volt line, there is a second marker. It sits at roughly 1.48 volts.
Right, the sources label this the thermoneutral enthalpy voltage.
If 1.23 is the floor, why do we have this second number? What's the difference there?
It is the difference between pure electrical work
Yeah.
and the total energy required by the system, which actually includes heat.
Heat?
Yeah, when you split water, you aren't just moving electrons around. You are changing the entropy of the system.
Because you're taking a liquid and turning it into two gases.
Precisely. Gases are more chaotic, they have higher entropy, and driving that physical change requires heat energy.
So the 1.23 volts is just the electricity, but the reaction also wants to suck in heat from its surroundings.
Exactly. If you somehow manage to run an electrolyzer perfectly at 1.23 volts, it would actually freeze itself solid
Yeah.
because it would pull ambient heat from the room just to make up the energy deficit.
So the 1.48 volt line, the thermoneutral enthalpy voltage, that represents the point where the electricity you put in covers both the work of breaking the bonds and the heat required.
Yes, at 1.48 volts, the system is in perfect thermal balance. It doesn't freeze, it doesn't overheat.
Okay, that makes sense. So 1.23 is the electrical floor, 1.48 is the total thermal electrical balance. But where do the actual machines operate?
In the real world, you mean?
Yeah, when a major energy company builds a giant gigawatt electrolyzer plant, what voltage are they actually pushing through the system?
They are operating significantly higher than 1.48. On the diagram, everything above that 1.48 volt line is shaded in this vast warning-colored amber zone.
The amber zone, and the text labels the zone the practical operating zone.
Right, and this introduces a concept that's going to dominate the rest of our discussion. Overpotential.
Overpotential, that sounds expensive.
Oh, it is. It is arguably the single most important word in the hydrogen economy.
What does it mean practically?
It represents any voltage you have to apply beyond that theoretical thermodynamic floor just to force the reaction to happen at a practical commercial speed.
The manifesto literally defines overpotential as kinetic waste.
Kinetic waste, meaning energy that does absolutely nothing to help split the water, it just gets lost.
Where does it go?
It is lost to sluggish microscopic kinetics. It is lost to electrical resistance in the wiring in the water itself, and a lot of it is just dissipated as waste heat.
It is a penalty you pay for the inefficiency of reality.
That's exactly what it is.
And I want to push back on this a little bit on behalf of the listener, because we are constantly bombarded by tech news, right?
Sure, the hype machine never stops.
We see headlines every single week. Stanford researchers discover revolutionary new water splitting technique, or startup uses quantum acoustic vibrations to split water for free.
Right.
So if I invent a miraculous new magnetic field or a pulsed laser or some ultra-advanced frequency generator, the sources are telling me I still can't get under that 1.23 volt floor. I can't hack the system.
You cannot hack the system. And this is where so many investors lose millions of dollars. The thermodynamic floor is an unavoidable closure lift cost.
It's locked in.
It is exactly like gravity. If you want to lift a 1-ton block of stone 10 feet into the air, there's a mathematical minimum amount of physical energy required to fight gravity.
Right. You cannot invent a magical new pulley that requires less total energy than gravity demands.
Exactly. You can change the gearing, you can change how fast you lift it, but the total energy debt to the universe is identical.
That is such a clarifying way to look at it.
And if we connect this to the bigger picture of global energy policy, the true technological frontier, the place where every scientist, engineer, and venture capitalist should be focusing their resources, lies exclusively in reducing that amber zone.
The kinetic waste.
Yes, the entire global race in hydrogen research is simply a fight to eliminate kinetic waste, to crush the overpotential as close to that 1.48 volt line as possible.
It is never about magically lowering the blue floor.
No, you cannot negotiate with thermodynamics.
All right, so if the entire game is about crushing that amber zone of waste, we need to know what's causing it. We need to figure out which part of the machine is bleeding all this energy.
We need to find the bottleneck.
Exactly. Who is the villain of this story? And according to the sources, the villain is indisputably the oxygen evolution reaction bottleneck.
To understand this bottleneck, we really have to look at the microscopic mechanics inside the machine.
Walk us through it.
So a water electrolyzer has two sides, right? Two electrodes submerged in the liquid. You pass a current between them.
Okay.
At the cathode, you have the hydrogen evolution reaction, or AR. That's where the hydrogen gas bubbles up.
The part we actually want.
Right. And at the anode, you have the oxygen evolution reaction, or OER. That's where the oxygen gas bubbles up.
And the sources spend almost this entire chapter emphasizing that these two sides are not symmetrical. They are not equally difficult.
Oh, not even close.
Right.
The hydrogen side is relatively straightforward, but the oxygen side is a microscopic nightmare.
A nightmare.
The manifesto identifies the oxygen anode as the central anchor dragging down the entire system's efficiency.
The text keeps calling OER a highly demanding closure reconstruction. Let's build a mental model of why this is so demanding.
Sure.
Think of the electrode surface as a highly exclusive, crowded dance floor. The water molecules are the guests outside.
I like this.
The hydrogen reaction on the other side of the club is simple. You take 2 protons, hand them 2 electrons, they pair up instantly, and they leave the club as hydrogen gas. Fast, easy.
Very simple choreography.
Right, but the oxygen side.
Really?
The oxygen side is like trying to choreograph a highly complex tango on that crowded dance floor. But the dancers actively repel each other, the bouncers keep interfering, and the floor is constantly shaking.
That is a remarkably apt mechanistic metaphor. Let's walk through the 4 distinct steps of this oxygen evolution reaction. Because when you look closely at these steps, you immediately understand why we have to pump so much extra voltage, so much overpotential into the system just to force it to work.
Okay, let's walk through the choreography. Step 1.
Step 1 is proton adsorption. A water molecule has to physically approach the metal surface of the anode.
It has to get onto the dance floor.
Right. And the surface, the bouncer, in your metaphor, has to grab that water molecule, hold it in place, and violently strip away an electron and a proton.
So you've ripped the coat off the guest. Step 2.
Step 2 is the formation of oxygenated surface intermediates.
Intermediates.
Yeah, you now have this fragmented piece of the molecule, an OH group, or a single oxygen atom clinging to the metal surface.
Just stuck there.
Yes. It is highly unstable, highly reactive, and incredibly irritated. It wants to bond with something, but it is physically stuck to the floor.
So we have these angry, isolated oxygen atoms covering the dance floor. Step 3.
Step 3 is the absolute crux of the problem. OO bond formation.
The tango.
The tango. You have to take that highly unstable oxygen fragment stuck on the surface and somehow perfectly coordinate its geometry with another oxygen atom.
Either from a new water molecule floating by or another fragment on the floor.
Exactly. You have to force them to pair up to make an O2 molecule.
But wait, why is that so hard? I mean, they're both oxygen. Shouldn't they want to bond?
You'd think so, but no. It's incredibly difficult because of electron repulsion and spin states.
The spin states.
Yeah. You are trying to force 2 highly electronegative, electron-dense entities together. The geometry has to be perfect down to the pentameter. The energetic states of their electrons have to perfectly align.
So they're actively fighting each other.
Yes. And it requires the simultaneous movement of multiple electrons and protons across the interface. If the atoms are too far apart on the metal surface, they can't reach each other. If they are bound too tightly to the metal, they can't turn to face each other.
It is a massive coordination problem. And finally, step 4.
Step 4 is O2 molecule release. If you actually manage to overcome all that and successfully form the oxygen molecule, it has to let go of the metal surface and float away as a bubble.
Because if it doesn't leave, the dance floor is full and no new water can get in. So, because this 4-step choreography is so agonizingly complex, the sources outline 4 specific diagnostic modules of waste. 4 ways this process bleeds our electrical energy.
Right. If you want to know exactly what the amber zone is made of, it's made of these 4 failures.
The first one is sluggish kinetics.
Sluggish kinetics.
Oh.
Because those 4 steps are so complex, the overall rate of reaction naturally wants to be very, very slow. The electron-proton coupling just takes time.
So to speed it up to a commercially viable rate, you just crank up the voltage.
You use brute electrical force to push the reaction faster. And that brute force is pure kinetic waste.
Okay, and the second waste module is adsorption traps. This relates directly to the bouncer holding the guests, right?
Yes. If the metal surface of the electrode doesn't hold on to the intermediates tightly enough, the water molecules just bounce off and the reaction never activates.
But if it holds too tight?
If the metal holds on to them too strongly, the surface becomes permanently coated in trapped oxygen fragments. They get stuck on step 2. The active sites are completely blocked, and the entire system just suffocates.
And even if you get the chemical bonding perfect, you still run into the third module of waste, which is physical blockage.
Which is an incredibly mundane physical problem. Bubbles.
Just bubbles.
Just bubbles. Then, when you finally execute step 4 and make that oxygen gas, it forms microbubbles on the surface of the electrode.
Okay.
If those bubbles don't detach immediately, they form a microscopic layer of insulating foam. Electricity cannot flow through a pocket of gas as easily as it flows through liquid water.
So to push the electrical current across that bubble layer,
You guessed it. You have to crank up the voltage again.
pumping more waste into the amber zone. And the fourth module is electrical resistance, which is just the inherent difficulty of moving ions through the liquid and electrons through the metal wiring. So taking all of this in, the picture becomes incredibly clear. The massive amount of extra electricity we pour into these machines isn't making us more hydrogen.
No, it's not.
It's almost entirely being used to bully this difficult, stubborn oxygen reaction into happening.
That is the tragic reality. This is why researchers spend an overwhelming majority of their careers obsessing over the anode. The hydrogen side basically takes care of itself. The oxygen side is where the war is fought.
Which brings us to the weapons used in that war. The gatekeepers.
The catalysts.
Right. If the oxygen reaction is holding the entire global hydrogen economy hostage, how do scientists clear the bottleneck? They use catalysts. But as our sources in the Lillian Manifesto clarify, the public fundamentally misunderstands what a catalyst actually does.
They address this directly as myth 3, the belief that catalysts somehow inject or create energy.
Right. It's treated like magic fairy dust. You sprinkle some platinum into the water and suddenly it just splits itself.
The closure theoretic framework provides a much more accurate mechanical definition. Catalysts are closure pathway modifiers.
They modify the pathway. They don't change the destination.
Exactly. They do not change the total energy required by the system. What they do is reduce the activation energy required to start the reaction.
The sources use the phrase, lowering the closure opening threshold. Can we visualize this?
Let's use a classic thermodynamic visualization. Imagine a massive mountain range separating two valleys.
Okay, I'm picturing it.
In the lower valley, you have liquid water. In the higher valley, you have your separated hydrogen and oxygen gases.
And the thermodynamic floor, that 1.23 volts, is the physical difference in elevation between the lower valley and the higher valley.
You have to lift the water up to that new height. There is no escaping that climb.
You can't magically lower the elevation of the destination valley.
Right. But between those two valleys is a massive mountain peak. That peak is the activation energy.
Ah.
To get from the lower valley to the upper valley, normally you have to push your boulder all the way up over the very top of that mountain and then let it roll down a bit into the higher valley.
That massive climb over the peak is the oxygen evolution bottleneck. It's the energy it takes to rip the molecules apart before they reform into gas.
Exactly.
So what does the catalyst do?
A catalyst brings a tunnel boring machine.
Oh, I love that.
It carves a direct tunnel right through the middle of the mountain. It provides an entirely new, lower energy pathway to get from Valley A to Valley B.
It doesn't change the starting elevation, and it doesn't change the final elevation.
It changes absolutely nothing about the thermodynamic destination, but it drastically reduces that massive, unnecessary spike in effort needed to make the trip.
And the secret to carving the perfect tunnel is a concept the sources call kinetic resonance matching.
Yes, kinetic resonance matching.
They provide this fascinating graph of absorption energy to explain it, and it looks exactly like a steep symmetrical bell curve. What are we looking at here?
This curve is the holy grail for material scientists. It's known as a volcano plot.
A volcano plot.
Yeah, and it visually explains the Goldilocks zone of chemistry we mentioned with the dance floor metaphor. On the horizontal axis, you have absorption energy. Literally how strongly the catalyst grabs onto those oxygen fragments.
And on the vertical axis,
You have activity, how fast the overall reaction happens.
okay, so on the far left side of the bell curve, the catalyst is too weak.
Exactly. The binding energy is too low, the bouncer is too weak, the water molecules just bump into the catalyst and drift away. The reaction fails to activate because the catalyst can't stabilize the intermediates.
And on the far right side of the curve, the catalyst binds too strongly.
This is the adsorption trap. The bouncer grabs the guest and refuses to let go. The oxygen fragments stick like superglue. They never form OA bonds. The surface is completely paralyzed and the reaction suffocates.
But right in the middle, at the absolute peak of that volcano curve, is kinetic resonance matching.
That is the Goldilocks zone. The ideal catalyst naturally sits at the exact peak of that curve.
It perfectly balances the two extremes.
Right. Its atomic structure perfectly aligns with the intermediate steps of the oxygen reaction. It grabs the water firmly enough to rip it apart, but it holds the resulting fragments loosely enough that they can slide around, find each other, bond together, and float away.
It smoothly guides the entire transformation, maximizing what the text calls the closure coupling coefficient.
Exactly. So the entire field of catalyst research is just systematically hunting for materials that naturally sit at the exact peak of that curve.
And the sources provide a material horizons table that details exactly what scientists are actually using today. Let's look at this, because the materials change entirely based on the environment.
Yes, the chemical environment dictates everything. The table breaks it down. For alkaline electrolyzers, which use a basic IPH liquid environment like potassium hydroxide, the current global champions for the oxygen reaction are nice layered double hydroxides.
Knife LDH, nickel and iron. That sounds incredibly common.
It is. They are earth-abundant, dirt-cheap, and their crystalline structure naturally hits that kinetic resonance peak for oxygen evolution in an alkaline bath. They are phenomenal tunnel carvers.
But then the table shifts to PM systems, proton exchange membrane OER. This is a totally different environment, right?
Completely different. PM systems operate in highly acidic, highly oxidizing conditions. It is a microscopic torture chamber for metals.
A torture chamber.
Yeah, if you put that cheap nickel-iron catalyst into a PM electrolyzer, the acid would dissolve it into metallic soup within minutes.
Oh, wow.
So for acidic systems, the table notes low-iridium architectures.
Iridium. I know iridium is used in spark plugs and like meteorites, but it is unbelievably rare.
It is one of the rarest stable elements in the Earth's crust.
Hmm.
But it is one of the only materials on the periodic table that can survive the brutal acidic oxidation of a PM anode while still naturally sitting near the peak of that kinetic resonance curve.
It can survive the environment and it can catalyze the reaction, which raises a massive red flag for me. If we are trying to build a global hydrogen economy to replace fossil fuels, and our best acidic technology relies on one of the rarest elements on Earth, aren't we just trading a fossil fuel bottleneck for a rare earth metal bottleneck?
That is exactly the crisis facing the industry. And it's why the table specifically specifies low-iridium architectures.
So they're trying to use less of it.
The cutting edge of science right now isn't finding a replacement for iridium. It's figuring out how to build microscopic scaffolds that stretch a single atom of iridium across as much surface area as possible to use as little of it as humanly possible.
Okay, what about the other side, the hydrogen side, the HER? What catalysts are they using there?
Because the hydrogen reaction is so much easier, just snapping the two Legos together, the table points to transition metal phosphides, or alloys like nickel molybdenum, NEMO.
So no rare earth metals there?
No, these are non-precious metals that are highly effective at forming that simple HH bond. We don't need platinum or iridium on the hydrogen side anymore.
Okay, let me pause and ask a practical question.
Sure. If I'm scrolling through a science news feed and I see an article claiming, university team discovers cheap new catalyst made of rust and soot that completely revolutionizes water splitting. Is that the whole story? Have they solved the energy crisis? Or have they just found a slightly better bouncer for the dance floor?
This raises a profound question about how we define a breakthrough. The Lillian Manifesto is explicit here. A catalyst merely lowers the gate. It lends temporary stability to an unstable reaction.
Temporary stability.
But a tiny speck, a perfect catalyst, sitting in a beaker of sterile, perfectly purified water in an air-conditioned laboratory is utterly, completely useless for the global energy economy.
Because it's not a machine yet, it's just a material.
Exactly. Activity without persistence is a parlor trick. And that leads us directly into the reality check of Section 5, building the machine.
Because a catalyst has to be integrated into a physical architecture that can actually survive years of industrial punishment.
Right, you can't just dump iridium powder into a vat of water and hook up jumper cables. The sources provide this incredibly detailed, integrated architecture schematic that breaks a real-world electrolyzer down into 4 critical codependent components. Let's build the machine for the listener. Component 1 is the catalyst.
As we discussed, the catalyst is the gate. It provides the tunnel through the activation energy mountain.
Component 2 is the support, and the text refers to this as the scaffold. Why do we need a scaffold?
You don't build an electrode out of solid blocks of catalyst. It'd be incredibly expensive and inefficient because only the atoms on the very outer surface would touch the water.
Right, the inside would just be wasted material.
So instead, you disperse microscopic nanoparticles of the catalyst over a high surface area material, like carbon nanotubes or a titanium mesh. That is the scaffold.
And what does it do, practically?
The scaffold does 3 things. It provides the physical structure so the nanoparticles don't clump together. It anchors them against the violent flow of the liquid. And critically, it acts as the conductive highway to deliver the electrical electrons from the wire directly to the catalyst particle.
Okay, so component 3 is the membrane, known as the boundary.
The membrane is arguably the most complex piece of polymer engineering in the machine. It sits right down the middle, separating the hydrogen-producing cathode from the oxygen-producing anode.
And its job is deeply contradictory, isn't it?
Very much so. It must allow charged ions, like protons or hydroxide ions, to easily flow through it to complete the electrical circuit. But it must act as an impenetrable brick wall to gas molecules.
Hmm.
It has to strictly enforce the separation of the hydrogen gas and the oxygen gas.
And finally, component 4 is the electrolyte, or the transport field.
This is the liquid, the acidic or alkaline bath, or sometimes a solid polymer matrix that surrounds the electrodes. It is the fluid medium that provides local charge transport and delivers the water to the catalyst.
Okay, so if we zoom out, what does this integrated architecture mean for our imaginary university lab with their miracle catalyst? It sounds like putting a flawless, one-of-a-kind Formula One engine into a chassis made of wet cardboard.
That's exactly what it is.
If you have the greatest catalyst in the world, but your scaffold rusts away in a week, or your transport field dries up, or your boundary membrane gets a microscopic tear in it, the entire multi-million-dollar device is a total loss.
That is the core argument of this section. Philip Lillian emphasizes that a true technological breakthrough is an integrated architecture, not an isolated material.
And the sources focus intensely on the failure modes of this architecture, particularly the third component, the membrane. They dedicate a lot of time to boundary integrity and durability.
Because if the boundary fails, the consequences aren't just a drop in efficiency. The consequences are catastrophic.
The text calls this failure mode crossover.
Crossover occurs when the membrane weakens or thins out or gets punctured by a localized hotspot, and the pressurized hydrogen gas leaks through the barrier to the oxygen side, or vice versa.
In the vocabulary of closure theory, crossover is closure collapse.
Yes, because the entire point of this massive, expensive, energy-intensive process was to separate the atoms, to create separated chemical potential.
The value of hydrogen lies entirely in its separation from oxygen.
If that separation is lost inside the machine, you no longer have stored energy. You have an explosive recombination hazard.
Oh, wow.
If enough hydrogen gas crosses over and mixes with the oxygen gas inside the pressurized anode chamber, a single static spark, or even just the catalytic surface of the electrode itself, will cause the gases to violently recombine. The system will literally detonate.
So the membrane doesn't just manage fluid flow, it is the physical guarantor of the stored energy's value.
And its safety. And the other side of that survival coin is durability.
The sources define durability in a very specific way. They call it the preservation of catalytic identity under repeated closure stress. What does catalytic identity mean here?
Well, we have to remember that the inside of an operating industrial-scale electrolyzer is an active war zone. It is not a gentle environment. The internal materials are subjected to high electrical voltage, extreme pH levels, intense localized heat, and the constant violent physical scouring of millions of microbubbles expanding and tearing themselves away from the surface 24 hours a day.
It's like continuously sandblasting your delicate nanoscale catalyst.
Exactly. And under that relentless stress, catalysts suffer what the text calls identity loss. They physically change.
How so?
The metal atoms dissolve into the acidic liquid and wash away. The surface oxidizes into a useless crust. The nanoparticles break loose from the carbon scaffold and float away, or they migrate and clump together into giant useless lumps, a process called agglomeration.
So they lose the specific atomic structure that made them special in the first place.
Precisely. This is why a material that demonstrates record-breaking efficiency for 20 minutes in a sterile lab beaker means absolutely nothing.
If it loses its catalytic identity after 2 weeks inside a pulsating, vibrating, hot industrial plant, it is commercially worthless.
Which brings us to an even messier, uglier reality.
Right, because we have the physics mapped out, we understand the architecture, we know we need durability. Now we want to scale up.
We want to deploy this technology globally.
We want to build gigawatt-scale hydrogen plants to replace oil refineries. And doing that requires astronomical volumes of water. You can't feed a gigawatt plant with sterile, double-distilled, deionized laboratory water.
No, the economics forbid it entirely.
Yeah.
To reach global scale, you have to use the water that is actually available. River water, industrial wastewater, or ultimately ocean water.
And this brings us to a fascinating segment of the manifesto, the challenge of impure reaction fields.
The sources detail exactly why seawater electrolysis, for example, is so brutally, punishingly difficult. They describe seawater not as water, but as a crowded reaction field.
A crowded reaction field. It is a chemical free-for-all.
It really is. When you take your perfectly tuned, delicate, integrated architecture and plunge it into raw seawater, you are introducing a massive threats matrix to the system.
Because seawater isn't just H2O. It is a complex chemical soup. Let's break down this threats matrix. The first and arguably most destructive threat, chloride ions.
Seawater is roughly 3.5% salt, mostly sodium chloride. The fundamental problem here is thermodynamic bad luck.
Bad luck.
Yeah, the electrical voltage required to oxidize chloride ions into toxic, corrosive chlorine gas is incredibly close to the voltage required to oxidize water into oxygen.
So the machine can't tell the difference.
It struggles to. The chloride ions swarm the anode, actively competing with the water molecules for the catalyst's attention. They cannibalize your electrical current.
Oh, no.
So instead of making pure oxygen on the anode side, you start making massive amounts of chlorine gas.
And chlorine gas is highly reactive.
It will aggressively attack and dissolve your catalysts, corrode your carbon scaffolds, and chemically destroy your delicate polymer membranes. It literally eats the machine from the inside out.
That's a nightmare. And that's just the first threat. Threat number 2, magnesium and calcium.
This results in physical scaling. When an electrolyzer operates, especially an alkaline one, it naturally creates localized areas of very high pH, highly basic zones right near the surface of the electrodes.
Okay.
Seawater is full of dissolved magnesium and calcium ions. When those ions hit that high pH zone, they undergo a rapid chemical reaction and precipitate out of the liquid as solid hydroxides.
They turn into rocks.
Literally. They form a thick, chalky, impenetrable crust over the surface of your expensive catalyst. It physically blocks the gate.
The water molecules can't even reach the tunnel boring machine anymore because it's buried under a layer of scale.
And the current drops to zero.
And threat number 3, biological material.
Chemical poisoning and physical fouling. Seawater is alive. It contains microorganisms, bacteria, algae, and dissolved organic debris. When you pump that through an electrolyzer, the bacteria colonize the warm, wet surfaces. They form biofilms over the electrodes, killing your active surface area. The organic debris clogs the microscopic pores of the boundary membrane, causing immense physical pressure and chemical stress until it ruptures.
So looking at this threats matrix, the machine has to somehow perfectly split water while actively repelling chloride, surviving chlorine gas, avoiding solid shock formation, and fighting off bacterial colonies.
Which is why Philip Lillian notes a very pragmatic reality. From a purely economic standpoint, pre-treatment running the seawater through a commercial desalination or reverse osmosis purification plant before it ever touches the electrolyzer is almost always cheaper and more reliable than demanding material scientists invent an impossible, omni-tolerant super machine.
Because it just can't magically survive raw ocean water.
Right. Desalination only adds a fraction of a cent to the cost of a kilogram of hydrogen.
But what if we didn't have to fight that battle at all? What if, instead of trying to purify the water or build an invincible machine, we just changed the fundamental rules of the chemistry?
This is where the sources introduce what I think is the most elegant, genius workaround in the entire manifesto: hybrid electrolysis.
Oh, it is a brilliant lateral move. It sidesteps the hardest problem entirely. Let's trace the logic for the listener.
Let's do that.
We established earlier the oxygen evolution reaction, the OER, is the central villain. It's the bottleneck. It causes all the kinetic waste. It requires the expensive iridium catalysts, and it's the hardest part of the choreography.
Yes.
So why are we doing it? Why not just skip the oxygen part?
Exactly. Ask yourself, what is the economic value of producing oxygen gas? Almost zero.
We are surrounded by an atmosphere made of 21% oxygen. Industrial oxygen is cheap.
We're fighting the hardest battle in thermodynamics to produce a byproduct that nobody wants.
So how does hybrid electrolysis bypass the OER bottleneck?
By replacing the water at the anode with alternative feedstocks. Remember, an electrolyzer just needs an oxidation reaction at the anode to balance the reduction reaction at the cathode. It doesn't strictly have to be water.
So instead of forcing the anode to perform the agonizingly difficult high-energy task of ripping water apart to make oxygen,
you feed the anode a chemical that is much, much easier to oxidize.
and the sources provide a feedstock module listing these alternatives. They list urea, alcohols, aldehydes, biomass-derived molecules, waste organics, and glycerol.
Right. Let's take urea as an example. Urea is a major pollutant found in agricultural fertilizer runoff and municipal wastewater.
Okay.
The thermodynamic voltage required to oxidize urea is significantly lower than the voltage required to oxidize water.
So wait, instead of using massive amounts of energy to purify seawater just to fight a brutal battle to make worthless oxygen, we can deliberately pump toxic agricultural wastewater into the machine, clean up the environment, and get our pure hydrogen fuel using less electricity.
Yes. If we connect this to the bigger macroeconomic picture, this is a massive paradigm shift in chemical engineering. By substituting the oxygen reaction with the oxidation of organic waste molecules, you drastically lower the total operating voltage of the system.
You shrink the thermodynamic mountain,
You are literally slashing the electrical energy bill of your hydrogen plant.
and you gain a dual value stream.
Precisely. On the cathode side, you are still happily bubbling off pure separated hydrogen gas for your energy needs. But on the anode side, instead of venting worthless oxygen, you are doing something highly valuable.
You are either performing environmental remediation like breaking down toxic urea, or you are performing chemical synthesis.
Chemical synthesis, like making actual products. You can feed cheap, low-value biomass like glycerol into the anode, and the oxidation process will convert it into high-value commodity chemicals used in the pharmaceutical or plastics industry.
The sources call this a coupled electrochemical transformation. It totally changes the business model.
It moves us away from a primitive, brute force water splitting model and into what Lillian describes as a sophisticated closure economy.
You are fundamentally changing the economic viability of the entire plant because producing hydrogen fuel is now just one half of a highly profitable paired industrial transformation.
That is mind-blowing. It turns the problem into the solution.
But with all these incredible new hybrid pathways and all the different catalyst architectures we've talked about, it brings up a really practical problem for the listener.
How so?
How do we evaluate what is actually real? When a company claims they've achieved a breakthrough, how do we spot the true innovations amidst all the noise, the skewed data, and the aggressive press releases?
That is the exact clinical purpose of Section 7, the truth about breakthroughs. To protect against the hype, the manifesto provides a 6-metric comprehensive performance metrics dashboard.
It is designed to act as an unforgiving reality check for any new technology.
I love this.
Yeah.
Let's role-play this for the listener so they can see how this dashboard works in practice.
All right, let's do it. I am going to be a slick startup founder. I walk into your venture capital office, I slide a glossy iPad across the table, and I say, "We've done it. A revolutionary new catalyst. It operates at an incredible current density. We hit 2,000 milliamps per square centimeter. It's incredibly fast. I need a $50 million seed round." How do you use the dashboard to interrogate me?
Well, first of all, I'm keeping my checkbook closed. You only gave me 1 metric out of 6.
Oh, come on.
Current density metric 3 on the dashboard is the rate of closure conversion per area. It tells me how fast you're making gas per square centimeter of your electrode.
Which is good, right?
It's important because if your current density is microscopic, I would need to build an electrolyzer the size of a football stadium just to power one factory. So high current density is good, but it means nothing in isolation. So I will ask you, at that high speed, what is your overpotential? Metric 1.
Overpotential, right. The kinetic waste.
Yeah.
The excess voltage pushed into the system beyond the thermodynamic floor. Okay, I say. Our overpotential is slightly high, maybe 400 millivolts, but look how fast it is.
Okay, so you are driving the system incredibly hard and wasting a lot of electricity as heat to get that speed. That brings me to metric 2, Faradaic efficiency.
What's that measure?
This measures the selectivity of your reaction. Out of all the electrical current you are violently pumping into this machine to get that high speed, what percentage of those electrons are actually yielding the desired hydrogen gas? If your Faradaic efficiency is only 60%, it means 40% of the electricity I'm paying for is just doing something else.
Like what?
Driving a parasitic side reaction, dissolving the electrode, or just making hot water.
Okay, you're cornering me, but I pivot. Fine, our Faradaic efficiency is a perfect 99%. We are making pure hydrogen at blistering speeds.
Impressive. But at those blistering speeds and high voltages, how long does the machine survive? Metric 4, stability hours.
Durability.
This measures the persistence of system identity under stress. You tested this in the lab. Did you run it for 10 hours, 100 hours, or 10,000 hours? Because an industrial plant needs to run for 5 years without replacing the core stacks. If your miracle catalyst dissolves into sludge after a week of high current operation, your technology is worthless to me.
We have proven stability for 5,000 hours, I claim defensively.
Okay, assuming you actually have the independent testing data to prove that, I still have a major safety concern. Metric 5, crossover rate. You are producing gas incredibly fast. How well is your boundary membrane handling that pressure? Is hydrogen leaking through the membrane to the oxygen side?
Right, because if it crosses over,
Because if your crossover rate exceeds the lower explosive limit, usually around 4% hydrogen and oxygen, your machine isn't an electrolyzer anymore. It's a bomb.
the boundary failure risk, you have to prove the separation is maintained.
Yes. And if, by some miracle, you can satisfy me on overpotential, Faraday efficiency, current density, stability, and crossover, we finally arrive at the ultimate judge of reality. Metric 6, LCOH.
LCOH, the levelized cost of hydrogen. This is the holy grail metric.
It is the only number the macroeconomic world actually cares about. LCOH is the final, delivered cost of the separated closure potential, usually measured in dollars per kilogram.
It mathematically integrates everything.
It factors in the capital cost of building the machine, the daily cost of the electricity you're using, the lifespan and replacement cost of your catalysts, the maintenance downtime, the water purification, everything.
So if your brilliant, high-speed, stable electrolyzer relies on a catalyst made of pure platinum and iridium,
Your capital costs will be so astronomically high that your LCOH will be $15 a kilogram. And no one will ever buy it because they can get dirty hydrogen from fossil fuels for $2 a kilogram.
that is the ultimate BS detector. The text provides a crucial warning here. A breakthrough cannot be defined by a favorable number in a single metric. One optimized metric almost always hides a systemic weakness.
We see this constantly in science journalism and venture capital. A lab optimizes for a cheap material, but completely ignores the catastrophic failure in stability. Or they optimize for speed, but sacrifice Faradaic efficiency.
Knowledge is most valuable when understood and applied holistically. You have to satisfy the whole dashboard to change the world.
Exactly.
Okay, so let's assume we do it. Let's assume humanity clears the board. We build the perfect integrated architecture. We master hybrid pathways. We hit the perfect LCOH.
We successfully, safely, and efficiently create massive oceans of separated hydrogen.
The final ultimate question of this deep dive is, where do we actually put it? What do we use it for?
And this brings us to the final chapter of the manifesto, Section 8, the endgame. Hydrogen as exergy logistics.
The sources emphasize this concept repeatedly to break our fossil fuel mindset. Hydrogen is not primary energy. It is a tool for moving energy.
It is the ultimate logistical tool. And Philip Lillian details how hydrogen is perfectly, uniquely suited to solve 3 specific macroeconomic bottlenecks in the renewable energy transition: the problems of space, time, and matter.
Let's start with space, energy transport.
The world's best renewable resources are almost always located far away from where people actually live. You have massive, blinding solar potential in the middle of the Sahara Desert or in the remote Australian outback. You have howling, consistent offshore wind potential 1,000 miles out in the ocean.
But you can't just build a copper wire from the Sahara to Berlin.
Exactly. Building a high-voltage electrical transmission line that long is incredibly expensive, geopolitically fraught, and physically inefficient due to transmission losses. The electrical resistance of the wire bleeds the energy.
So how does hydrogen fix that?
Well, if you use that desert solar power on site to split water and create hydrogen, you can compress that hydrogen into a pipeline or liquefy it and put it on a specialized tanker ship.
You are physically moving the separated closure potential across the map.
Hydrogen solves this spatial problem by detaching clean energy from the electrical grid. Next is the problem of time. Seasonal storage.
This is perhaps hydrogen's most vital, irreplaceable role. The fatal flaw of renewable energy is intermittency. The sun sets. The wind stops.
Now, lithium-ion batteries are phenomenal technology, but they are designed for short-duration storage, right? Hours, maybe days.
Right. They self-discharge over time, and building enough giant battery parts to power a major industrial city for an entire sunless winter month would require more lithium than exists on Earth. It is financially ruinous.
So how does hydrogen solve time?
Through immense chemical scale. In the middle of summer, when you have massive excess solar power that the grid doesn't need, instead of shutting the solar panels off, which we currently do, it's called curtailment,
Right.
you use that free excess energy to run massive electrolyzers.
You make hydrogen.
You pump the resulting hydrogen gas deep underground into massive salt caverns for storage. It will sit there indefinitely without losing a single joule of energy.
Then, in the dead of winter, when a multi-week freeze hits and solar output drops to zero, you pull that hydrogen out and run it through turbines to power the grid. Hydrogen preserves a closure potential across seasons. It acts as the strategic reserve for the power grid.
And the third problem it solves is matter, industrial chemistry.
Sometimes a wire just won't do the job.
Yeah.
You need to embed actual energy into physical materials.
Like what?
For example, direct electricity is useless if you need to synthesize ammonia to make global fertilizers. You literally need hydrogen atoms to combine with nitrogen in the Haber-Bosch process to feed the planet.
You can't make green steel with a battery either, can you?
No, you need a reducing agent, a physical molecule to strip the oxygen away from the iron ore. These heavy industrial chemical processes demand a molecule, not an electron. Hydrogen acts as the physical delivery vehicle to inject energy into matter.
To make this brutally clear, and to show where hydrogen does not belong, the sources provide a framework called the direct electrification hierarchy. It ranks exactly how humanity should be using its clean electricity, tier by tier.
It is a hierarchy of thermodynamic efficiency.
Tier 1 is direct electricity.
The golden rule of Tier 1 is always use electrons directly if possible. It is mathematically, unarguably, the most efficient use of energy to simply run a wire from a solar panel directly to a spinning motor, an LED light bulb, or a heat pump in your house. You lose almost nothing in translation.
Tier 2 is batteries.
The rule is use batteries when energy must wait for a few hours or move locally. This covers daily grid balancing, storing solar from noon to use at 8 p.m. It covers laptop computers, and crucially, it covers light passenger vehicles and commuter cars. The turnaround efficiency of a lithium battery is fantastic, around 85 to 90%.
Tier 3 is hydrogen.
The rule here is strict. Use hydrogen only when electrons cannot conveniently go, wait, or become chemistry. This is for the heavy lifting. Long-duration seasonal storage, transoceanic spatial transport, making ammonia, refining metals, and potentially heavy long-haul trucking where batteries are too heavy.
And Tier 4 is synthetic fuels.
This is the lowest tier of efficiency. You take your green hydrogen and you chemically combine it with captured carbon dioxide to make a synthetic liquid hydrocarbon, like e-kerosene.
So jet fuel.
Yes. You only use this when high-density liquid fuels are absolutely physically mandatory, specifically heavy maritime shipping and global aviation. You cannot fly a jumbo jet across the Pacific on batteries. It would be too heavy to leave the runway. You need the energy density of a liquid fuel.
Okay, looking at this hierarchy, I have to ask the obvious question. What does this all mean for the dream of the hydrogen-powered passenger car? You know, pulling your sedan up to the pump, filling it with hydrogen gas, and driving to work. Based on this hierarchy, is that entire concept essentially a dead end?
In the context of total system efficiency, a hydrogen passenger car is essentially thermodynamic sin.
A sin. Walk me through the math of why.
Imagine you have 100 kilowatt hours of clean solar energy. If you put that into a battery electric vehicle, you lose maybe 5% charging the battery and another 10% in the electric motor. You get roughly 80 to 85 kilowatt hours of actual forward motion at the wheels.
Highly efficient.
Now, take that same 100 kilowatt hours of solar energy and use it to power a hydrogen car. First, you lose 30% immediately during electrolysis, the overpotential waste we talked about.
Now you only have 70 units of energy left in the hydrogen gas.
Then you have to compress that gas to 10,000 psi to fit it in a car tank. Compressing gas takes massive energy. You lose another 10%. Now you're at 60. Then you have to put it in a truck and transport it to the gas station. Another loss. Finally, inside the car, the fuel cell has to convert that hydrogen back into electricity to turn the wheels. Fuel cells are only about 50% efficient.
So you lose another half of what's left.
Exactly. Out of your original 100 units of clean energy, you might get 25 or 30 units of forward motion at the wheels. You threw away 70% of your energy just managing the logistics of the molecule.
When a battery can do the same job with 85% efficiency.
Right. Using hydrogen for a commuter car is economically and mathematically irrational. The true, mature hydrogen economy does not look like a consumer product. It focuses exclusively on heavy industry and seasonal grid storage. It selectively uses the molecule only when electrons simply cannot do the job.
Which brings us full circle. We started this deep dive by unlearning the most seductive, persistent myth in energy, that water is a magical fuel waiting to be burned.
We replaced that extraction mindset with the reality of closure theory. We discovered the unyielding thermodynamic floor, and we navigated the brutal, microscopic choreography of the oxygen evolution bottleneck.
We learned how catalysts aren't magic pixie dust, but clever molecular gatekeepers that use kinetic resonance to carve a tunnel through the mountain of activation energy.
We saw how hybrid systems can bypass that mountain entirely by feeding on organic waste, turning a chemical hurdle into a dual-value environmental solution.
And we finally placed hydrogen in its proper realistic economic role, not as the gas in our passenger cars, but as the exergy logistics backbone of global heavy industry.
You now possess a closure-theoretic map.
You can see completely past the hype of free energy water engines, and you can truly appreciate the incredible, grueling, microscopic engineering required to build the actual future of energy.
It is a future built on respecting thermodynamics and mastering the closure loop, not hunting for the next magic well.
And I want to leave you, the listener, with a final mind-expanding thought to mull over as you digest all of this. If hydrogen's true destiny isn't replacing the gas in our cars, but rather serving as the logistical backbone for seasonal storage and global industrial chemistry, then the map of the future energy world is going to look completely different. It won't be dictated by who has the most oil under their sand or who controls the biggest coal mines. It will be dictated by who has the most optimal geography for generating massive amounts of cheap solar and wind, and who has the geological salt caverns to store massive reserves of chemical potential across time. Are we prepared for a geopolitical reality where energy security is completely detached from extracting finite natural resources and entirely dependent on mastering the logistical flow of the closure loop? It's something to think about the next time you look at a glass of water and realize you aren't looking at a geyser of free energy. You're looking at the foundational architecture of a brand new global power structure.